Today we're going to understand magnets and magnetic fields, and we're going to do it with hands-on demos of magnets and electromagnets. Today we're going to tackle the question, how do magnets work? Hello, welcome back. Today we're going to conquer the topic of visualizing magnetic fields. So we have several goals here. The first one is to talk about the magnetic field that surrounds a magnet and try to understand its shape on a sheet of paper, but also in 3 dimensions, so that we can move into our second goal, which is to talk about how magnets influence each other in terms of attracting and repelling each other. And then of course we're going to wrap it up. I have a bunch of test equipment here. We're going to drive an electromagnet, and we're going to understand how we can use electricity to generate magnetism in a magnetic field. Once we understand the permanent magnets and the shape of the field with several shaped magnets I have, and the electromagnet and how it generates a magnetic field, then we'll go to the board and we will start to write down sort of the current theory as to how magnets actually work. So we have to understand all of this before we can sort of understand how magnets actually function at the quantum mechanical level anyway. So the first thing we want to talk about is what everybody knows and is interested in, and that is that magnets attract and repel each other. So here I have 2 bar magnets. Notice I have a north and a south pole, and you can see that when we get them close together, these guys are, it looks a little bit better this way, that they repel each other. Notice that when you have south facing south, they repel each other, but when you turn it around to a north side of the magnet, then of course it doesn't repel each other anymore, it attracts each other. Now we have a little bit stronger magnets here. Look at these influence each other farther away, and they just look magical the way in which they work. So here we have the 2 north sides facing each other. If we put the 2 south sides facing each other, we get repulsion. So like sides of the magnet repel each other, but when we have a north facing a south side, it doesn't repel each other anymore, it attracts. So here we have a magnet attracting and repelling another magnet. If we turn them sideways, we can get similar behavior. South touching north, north touching south, they attract each other, and it's very strong, actually hard to pull apart. But if we turn this around so that we have south and south facing and north facing, then of course, this is really impressive and fun to do. They just totally repel each other. You can get, in this case, several centimeters of distance between them there. All right, the next thing I want to do is I want to put these aside. We're going to go back to our slightly weaker magnet here. And here we have, I have over here these disc magnets with a hole in them. And even though they're not labeled, there is a north and a south side. It's not labeled, but there's a north and a south side to this. And you can see that these are magnets also. Attract the magnet there. Now the interesting thing we can do is we can connect them like a car, and we can actually use the magnet underneath to sort of propel the wheels, so to speak, on the car. So let's see if we can get that to work. And if we kind of push it over here, there's a little bit of repulsion I'm feeling, but then when I get past it here, you can kind of see it kind of like scootering that way. So what's really going on is it's sort of it's attracting it here, and then when it gets to the middle of the magnet, I'm starting to feel a repulsive force, but when it gets over the hump of the repulsion, then it's kind of pushing it. You can see it kind of like oscillating back and forth right there. That's kind of neat too, actually. You can see that effect right there, because there's an attractive force right there. Out of the north pole of the magnet, there is an invisible field that is coming out of here and entering into the south pole. Right? You can't see it, but we see its effects by its attraction and repulsion of other magnets and other metals. And the field is actually coming out of the North Pole and entering into the South Pole. So the directionality makes it a vector field. We use the word vector, it just means it has a direction associated with it. So this field is pointing out of the North Pole, and it loops around and points in to the South Pole. All right, the next thing I want to do is pull out slightly different magnets. These are disc magnets. They're a little bit stronger, and they're hollow in the center, and they're pretty strong. And you can see how hard that I have to kind of pull to get them to come apart. Actually, it's very difficult. You mostly have to slide them here. So if I put this guy on the bottom here and then put this one on top, then I feel a repulsive force, and you can see it's basically levitating right there. Now what's neat about this is I can sort of bounce it up and down. I can feel it. It's like very springy. It's like a mattress or something. It's very springy like this. So what we have inside here are the same poles, either both north or both south, and that's why they're repelling each other like this. If I were to flip it over, and then they would be attracting, and they would have opposite poles, opposite attracts in terms of magnetic fields as well. All right, now I mentioned before to you that the magnetic field is exiting or coming out of the North Pole and then coming back around and connecting back in through the South Pole. One thing I want you to remember is that all magnetic fields have to form closed circles. Right? They don't just emanate from a point like electric fields do. They form closed loops always, right? And so here is the bar magnet. So that's what we visualize here. So here's another bar magnet into the shape of a cylinder. What I want to do is visualize this field in a three-dimensional shape. Here is iron filings. We're going to do a lot with iron filings, but here is just a fluid-filled box here full of iron filings. So with no magnet inside, you can see what's going on here. Let's drop this thing in here and see what happens. We'll drop it in there and look at what happens there. You can see the magnetic field immediately appear. In fact, it's a little more impressive if I close it off here, and you can see it sort of attracting inside of there now. And if I give it a nice little shake, and I'll try to get the angle with a couple of different cameras. So there's sort of a side view there. Let me kind of let it go so you can sort of see that. And then we'll do it with sort of the top view there. And so you can see that the field is exiting and coming around. You can see the curved nature of the field as it comes and sort of enters into the bottom. So we're going to draw more pictures, but I think this is like the best thing that I really want you to drill into your head. Look at how the field is very curved like that and kind of like angular and then going into the bottom. So if you can imagine these lines coming out of the top and then flowing into the bottom, then the next thing you need to know is that the magnet is the strongest, or the magnetic field is the strongest where these field lines are concentrated. So you can sort of see actually, well, let me go ahead and let it do its thing. But you can kind of see that the bunching up is starting to happen near the ends. So if you can imagine all of these lines entering into the pole, then they're all going to get crowded near the pole, either the North or the South Pole. And the more crowded or the more dense those field lines are, the stronger the field. I'll say that again. The more crowded or dense the magnetic field lines are, is where the magnet is the strongest. And you can kind of see it now that I've just sort of let it settle right here. You can see along the bottom a really nice curved, you can see that sort of the curved magnetic field's like less dense there, but near the poles everything is bunched up. That's because there's more field lines kind of concentrated there, and so a higher field strength. If you want to know the word of the day, which I love this word, when we talk about magnetic fields and electric fields also, we talk about the flux density. When you hear about something, you hear the term flux density, it just means the density of the field line. See, these lines are called magnetic flux. It's got a cool name, magnetic flux. So the flux density is just how many lines are in just like regular density, in a volume. Or you could talk about surface area if you're talking about the lines cutting through a surface area. So flux density, let's talk about field lines penetrating a surface area there. And so the flux density is highest where these field lines are entering into a pole because they're crowded and concentrated over a smaller area. But out away from the pole, they're more spread out, and so the magnet is less strong or less intense near the sides and more intense or more strong near the poles. All right, so far we've had magnets attracting or repelling other magnets. Now we also want to play with other situations here. So here we have some paper clips. These are coated, so they're colorful, but inside, of course, they're metal paper clips. And then we can take the magnets and actually, even though these are not magnetic, you can see they're not attracting each other, we can obviously use a magnet to lift them up. Now this is a pretty weak magnet, but still works pretty good. Let's grab our stronger magnet and see how that looks. We'll just kind of bring this down here, and we get a little closer, and of course we start to pick these guys up. And I think we even have a better magnet probably for this demo. These are already together, but we can just get it a little closer and we can immediately see, that's pretty neat. We'll do that one more time. So you can see that as the magnet is stronger, it can exert a force over a longer distance, a magnetic force. But what's interesting about it, so there are different materials that are able to be attracted by a magnet. We call those magnetic materials, and some materials are not, right? For instance, some examples. Iron is magnetic. Inside of this container is little filings of iron, little tiny chips of iron. That's why they're able to be influenced by the magnetic field. Nickel is another metal that's able to be magnetized or attracted by a magnet. Cobalt is another one. Also steel. Steel is able usually to be magnetized or to be attracted. Well, steel contains iron. And so that's the reason why. Or if it contains any magnetic material, if it's an alloy, right? But some materials are not able to be magnetized. For instance, copper is not able to be magnetized. Aluminum, if you get an aluminum can, it's not able to be magnetized either. All right, so here I have some copper wire. There's no insulation on this, so that's why it looks beautiful in copper there. We're actually going to use this wire later to make our to run an electric current and see the magnetic field that surrounds a wire. That's why I have it out. And here we have our paper clips. Now, if I run, of course, the magnet over the paper clips, of course, they attract. But I can run my magnet along the copper all day long, and nothing happens. It's not magnetic at all. This is the more strong magnet I have. It's just not affected by it at all. Aluminum is the same way. Now, I'm not going to explain in great detail why certain metals are able to be magnetized and aren't. I will tell you that all of magnetism is a quantum mechanical effect. It has to do with the electrons, which are in the atoms or surrounding the atoms, and specifically it has to do with what we call the spin of the electrons. I don't want to get too much into it now. I'll touch on it later. But there's a characteristic of electrons called spin. And when the spins are all aligned in the material, then we can magnetize the material, or if they're able to be aligned in the same direction, right? But when they're unable to be aligned, then you have random directions of electron spin, and so you don't see any observable magnetism from the outside, from a macroscopic point of view, from the whole substance. And copper and aluminum and some of the others are not able to be spin aligned from the outside like this, whereas whatever this paper clip is made of, probably steel or something, are the electrons that are in there. It's not magnetic now, but when we bring the magnet close to it, it's able to align the electron spins in these paper clips, and then so they become magnetized, and of course magnets can be attracted, and so it attracts, right? Now I have something else I want to attract and repel. I just think they're neat. Just another metal here. It's probably steel, although I didn't make them, so I don't really know. It's just fun. If you take this guy, of course you can attract them. And notice what's happening here. This is actually kind of interesting. Notice that let's look at the one on the end here. The one on the end is able to be attracted to the one next door. Even though the one next door, let's remove these two away from the magnet. Are these magnetic? No, they're not magnetic. So these two little discs here, they are not magnetic, right? But whenever they are touching one of the pieces that are touching the magnet, then they're able to turn into magnets. So what's happening whenever you attract a piece of metal is the magnetic field emanating from the permanent magnet, where I'll just give the punchline away. And the permanent magnet are materials where all of the electron spins are already aligned in the same direction, or a whole great many of them are aligned in the same direction. So the magnetic field can emanate and permeate the space around the permanent magnet. Whenever you have a material come into contact with that's able to be magnetized, then temporarily their electron spins can be aligned in the same way. So they can turn into magnets sort of temporarily when they're in the vicinity of the magnetic field. But when we remove these guys from the magnetic field, as they're all sticking together here, we can just kind of like pull them away, and then suddenly everything literally falls apart. They're not magnets anymore. So sort of a temporary effect. Now, since we're talking about magnetic attraction, we've picked up paper clips, we've picked up these little discs. Here is what we call iron filings. Now, we're going to use these a lot in just a few minutes to visualize the magnetic field here. But I do want to share with you and just show you how it's just sort of fascinating to watch. You bring a magnet near this iron, which is able to be magnetized, and you can just see it almost vacuuming it up like just like a vacuum cleaner. And you can kind of hang them off of. Notice that the iron, the pieces of iron that are attached to the bottom are temporarily magnetized, able to attract further pieces. So it's able to temporarily magnetize the iron. Now, eventually, the little stalactites, or whatever you want to call it, they get so long that they can no longer pick up anything else, because it has to be close to the parent magnet in order to be magnetized. So the effect does wear off. You can't build these things forever, but we can do some impressive things. Like, that's pretty neat. Now we can kind of hoover them all up here. Let me hold that down, and let's just pick them all up. That's just kind of neat to look at. You can just see the back and forth dancing that's going on here as we pick them up there. So we can kind of do that, and then we'll bring this to the side and we'll put that away and clean it up later. Now, the next thing we want to talk about is to try to visualize this, and we've used several ways. We want to just drill it home that there is some sort of invisible field around this, because if we have a compass, let me move the magnet away, this compass is going to point to the magnetic north pole of the Earth in my vicinity. So you can see it's kind of pointing off in that direction. So notice it's pointing in that direction. If I move it over here, it's pointing in the same direction. If I move it over here, same direction. Over here, same direction, because it's pointed to the strongest magnetic field that it feels, which is the Earth's magnetic field. So no matter where I move it, I mean, I'm wiggling it a little bit. Well, once it settles, it points in the same direction. Now, if I bring a new magnet here, there is a magnetic field emanating and permeating and surrounding that space here. And now, let me move this over here, and we'll put this over here. And what happens as we get closer to this magnet, right? You can see it's sort of locked in place. Let me move the magnet out of the way, and we can see that the effect that it has here. Let's move it over here. Now it's pointing to the magnetic north. As we put the magnet here, you can see it just changed. Now, as we move the magnet around here, you can see it's just locked on. It's locked on to what it sees nearby, because the magnetic field coming out of this thing is much, much stronger than the locally, because it's closer to the magnetic field of Earth. The magnetic field of Earth is strong enough to protect us from the solar wind, and it's a strong magnetic field. But locally, this magnet, since it's so much closer, is kind of overwhelming it here. Now, as we move farther away, it does continue to respond, but notice it's kind of like wiggling more. It's maybe not like quite as locked on. It's moving, but it's just not as locked on. When you bring this thing close, it is absolutely locked on to moving as we move around here. So I'm going to do the same thing when we do the electromagnet with the wire. We're going to do it with the compass. We'll do it with the iron filings to show you and prove to you that not only are permanent magnets able to be formed and created, but when we run an electric current through a wire, we're going to be able to measure and observe that there's a magnetic field surrounding the wire. That's going to be a huge clue as to how these magnets work, because if we can run an electric current through a wire and generate a magnetic field, then it's a good guess that maybe there's something to do with electrons inside the permanent magnet that's also generating the magnetic field. And we're going to connect those two things together as we go along in the further demos. So now what we want to do is visualize the magnetic field with sprinkling the iron filings. And so we're just kind of getting a little more, and we'll use different shape magnets as well. So here we have our north-south magnet. Remember, this is the one that's not so strong. So I'm going to place it under a sheet of paper, and I'll sprinkle these iron filings on top. And when we sprinkle the iron filings on top, hopefully we will see the magnetic field that this magnet has sort of like come into focus here. We'll get a few more on there. I can start to sort of see it now. Yeah, you can see that good. And you can give the paper a little, kind of a little shake, helps it also. Right? So you can see that here was the north pole of the magnet. You can even see the S for the south here. That the magnetic field is emanating from here and going and traveling around and entering in through the south pole. And the same kind of thing is happening right here. Right? This is very, very similar to what we already saw with our cube magnet. I'll put it right on top. In 3 dimensions, you can see it's happening going from north to south in 3 dimensions all throughout space there. This is just a flat representation of the same thing. So let's go and do the same thing again with our stronger bar magnet. All right, here's our stronger bar magnet, and we'll put it underneath, and we should basically see the same sort of thing, but I just want to give you exposure to what it looks like, but it should look a little more intense. We'll kind of like see. Notice how when we sprinkle it, we don't have to shake the paper. It's like immediately locking into place. It's like a really, really, really nice looking magnetic field here. And that's because this magnet is stronger. So as soon as the iron hits the paper, it's immediately magnetized and locked into place. We can give a little shaking here or whatever if we want to see it. But you can see how intense the magnetic field near is the north and the south here. All these field lines are coming and entering into the north and the south pole. The density or the flux density of the magnetic field dictates how strong the field is. So the field is strongest here, and it's weaker here. And of course, as you go farther out, the field lines are spread even more farther out, and so it's weaker out there. I have one more, even stronger bar magnet. We'll do that one next. All right, now this one's not labeled north and south, but there is a north and a south pole here. I just don't know which is which, but it's there. This is called a neodymium magnet, which is a rare earth magnet, and it's stronger than any of the other ones. So put that under there. Let's see what this looks like. We should see the same thing, but we should see it lock into place really, really quickly. Let's see. Notice that this one is so strong that we can't even really visualize the field that much. The reason you can't visualize the field that much is because it's attracting it so incredibly fast that you really can't see much of anything. It's just attracting it to it. Now you can sort of see the shape of it. You can see that it's radially coming out here. But again, it's so strong that it's just pulling it in immediately. So it's actually a little more fun to look at the other magnets. Now this one is actually so strong, I want to show you what happens when I lift it up. Just because of the iron there, I've actually lifted the magnet off of the underlying paper here. If I reach down below, it's actually attracted. It's not even going to come off the paper. You can see me trying to pull it. It's very difficult to pull it off. This is a really strong magnet. In fact, we can see what it looks like to try to suck these guys up over here. You can just see it, just like a vacuum cleaner. You can just pull it all up there. All right. All right, I have another cool toy here. This is iron filings inside of a sort of a transparent plate there, and there's sort of oil or fluid in there. And if you shake this thing up and just kind of get it going, then you can get it to evenly disperse throughout there. It's just different ways of visualizing things. If I'm going to do this, I want to do it right. I want to do it with a bunch of different ways to visualize. You're going to see the same thing, but it's just really neat to see this just sort of snap into place. Let's look at the magnetic field right there. And you can see that the magnetic field sort of snaps into place. You give it a little shake. Now remember, this is our less strong magnet. Actually, I think it's going to work better if we go this way. So let's go long ways here. We'll go right down on top of it, and let's see if we can see the magnetic field. And you can. Of course, you can see it emanating and coming from one pole into the other, from the north, coming out into the south, same sort of thing. Let's do the same exact thing with our slightly stronger magnet. We'll, again, go this direction. Now let's make it north-south like this. See what this looks like. Okay, we'll go right on top with it, and you can see it. You can see the magnetic field coming out. Notice it's so strong that you can't see it after a few minutes. So when you use this one, it's actually a little bit better to kind of keep it separated from maybe that far away. Then you can really see the field very, very, very clearly. And check it out. As you move it around, it's so neat to watch the field sort of propagate through the iron filings. In fact, that's so cool. I think we're going to do it again. So we start over here this time, and let's just sort of race through and watch the magnetic field propagate through and affect the iron filings that are above, like that. All right? Now, if you remember the really, really, really strong magnet, we had a hard time visualizing because it was attracting so kind of violently, for lack of a better word. So we'll do the same thing. We'll see how fast it happens. Boom. It's just done. It attracts it so fast you can't really see it. So what we can do to visualize it a little better is, because we couldn't really see it better before, we could just keep it separated from the top, like maybe this far away. Then it's still starting to suck it in from all directions. In fact, this one is so strong, it's emanating very far away, so we're going to see it better when we turn it lengthwise, like this. Well, let me mix these iron filings up a little bit more. Let's see if we can see it right there. You can see that magnetic field really, really, really clearly. Get a little closer, and you can just see it starting to suck it in there. So that's a neodymium magnet, which is a rare earth magnet. Okay, here's our disc magnet with the circle in the middle. Now, it's not labeled north and south, but I can tell you how this works is that one side of this disc is the north side, and the other side would be like the south side. Now, I don't know which is which, but one of them is north and one of them is south. So if you can imagine, the field is coming out of the north side and entering into the south side, but it's doing that all the way around. It's coming out of one side of the disc and going around to the other side, and also going through the center and reaching around as well. You can almost think of it like if this is the north pole here of a bar magnet, we know that the field comes out and into the south side. It's just this one is constructed in a way where we take the bar magnet, you make it really, really small, and then you make a disc of it. So it comes around like that. Let's see if we can visualize the magnetic field using our iron filings and see if we can see if our idea makes sense here. So we have the bar magnet there, or the circle magnet there, put some iron filings on top. Now it's going to be difficult to see the full extent of it because we're looking kind of down, right? As we said before, it's coming out of the top, going through the table and back through the bottom. So we're not really able to see. You would have to look from the side to be able to see the profile. Maybe we'll try it. I think it's going to be difficult to see, but maybe we'll try it anyway. And we can see that it's doing something like that. We can do the same thing with the fluid cavity. All right, here we go. Take two. We'll put this guy right on top, and we see, oh, that's so neat looking. It just sort of, you could just see it happen like in real time. We'll do that one more time. If I go all the way on top of it, it just happens too fast. I almost prefer to keep it far away so you can sort of see it happen. starts to attract those guys. You can see the middle clear out because it's just sort of stopping as the filings get to the edge. They're sort of stopping there. And so the field lines are coming out and going around to the other side. Now, I don't really know if this is going to work, but let's see if we can get this to work. I've never tried it, so I doubt it'll work, but I don't know. Let's just try it. Let's just try it. Let's see what it looks like when we do it from edge on. Oh, look at that. That worked way better than I thought. I hadn't actually tried this before. So you can see the magnetic field is coming out of one side and into the other side. So one side is north, the other side is south, or vice versa. We'll do the same thing, just for giggles, with the fluid-filled cavity. All right, here we have our disc magnet. We'll put it like that. We'll do our fluid-filled cavity and see what we can see. We'll get it close, and what do we see? Yes, it's exactly what we want to see. So we can see it kind of coming out and reaching around to the other side. So that is the shape of the field. Now you have to use your imagination because it's happening in 3 dimensions. All around the periphery, it's kind of coming out and also going through the middle and doing the same kind of thing there as well. All right, what other magnets do we have? We have a horseshoe magnet. This is a kind of a weak horseshoe magnet. When you see a horseshoe magnet, you need to think basically all that they've done is they take a north-south magnet here and they just literally bend it and they heat it up or something and they bend it into a horseshoe. So it's nothing, it's not like a different kind of magnet or anything. It's just a bent shape. And of course we can do it with our handy-dandy little visualizer right here. And we can see that the north and the south sides here, we have the most concentrated area there. And of course the north is kind of connected to the south in the same way that it is here. The field is coming out and into the other side, so of course it's going to come out and go into the other side there, but of course it also has to travel and go all the way around here, all the way around the magnet. It's a little bit weaker on the bottom side there. Let's try it with the iron filings. I haven't actually done this one, but we've got everything ready. And I have a stronger horseshoe magnet we can visualize as well. So we'll do the same thing here. You can see the field is definitely strongest between the ends of the north and the south. But if you can visualize it, it's kind of connected there, but it's also kind of going around very, very weakly down to connect to the other side as well. All right, here's our final horseshoe magnet here. We've got this one here. We'll go first from the top view here. What does our little magnetic plate here show us? Of course, this is a lot stronger, so we can see the flux density. The density of the field lines is much, much tighter there, or more concentrated, so we know that this magnet is stronger, and it is a stronger magnet. We'll look at it with the iron filings. I'm getting kind of efficient at this, so I can kind of got the hang of it there. Let's see what it looks like out here, away from it. So the field does, of course, go between. That's where it's strongest, but it does loop around and connect to the other side. So remember, magnetic field lines have to form closed loops. We'll do it from the side view, just to close it out and finish out this part. All right, so here we have the profile of the horseshoe magnet here. Again, we should see the north and the south connected together. We'll try it with this first, see what it looks like, and that's exactly what we see. The north and the south pole are connected by these field lines, and of course the lines go all the way around, but they're a little bit weaker as they get farther away. There. So we'll do the same thing, and this will be our last iron filing demo. A little sad, I know, but that's what we're going to do here. So you can see, same kind of thing. The way you read this is you say, all right, obviously it's stronger here where everything is concentrated, but as we get farther away, the field lines are a little more spread out, and so it's weaker, but ultimately it is connecting the north and the south pole, and all of these magnets form closed loops. Now, if there's anything I want you to get out of this portion of sort of the demos and the lesson here, is that magnetic fields always formed closed lines, right? And the closer the lines are together, the stronger the magnetic field is in that area. That means the stronger magnetic force is present on magnetic metals and other magnets. But the farther the spacing is between the magnetic field lines, the weaker it is. A better word for that is called flux density. Higher flux density means compacted, very tightly spaced lines, means strong magnet or strong magnetic field in that region. But over with low flux density means lines are spaced out, magnetic force, magnetic field is a little bit weaker. We talked about bar magnets, we talked about circle magnets, we talked about the compass and all of these things. Now we have to turn our attention to one of the greatest discoveries of the last couple hundred years, and that is that not only do some materials have magnetic properties and are magnetic. That was known for a long time. But the idea and the concept that electric currents also generate magnetic fields. So what we're going to do is turn the test equipment on. We're going to hook up an electric current through a wire, and we're going to see that the wire that's passing the electric current generates its own magnetic field surrounding the wire. All right, so here what we're going to do is bridge the gap between permanent magnets and magnetic fields generated by electric currents. It was one of the most important discoveries of the last couple hundred years that electricity flowing in a wire generates a magnetic field around the wire. We use this from everything from electric motors to generators, so very, very important. Here I have a piece of copper wire. I'll put it against the white background so you can see it a little bit better here. It's just supported there. And what I'm going to do is run an electric current through this. Now, I have to say this. I don't want anybody to ever try this at home because I have to put quite a bit of electric current through the wire in order for us to measure the magnetic field. Now, this isn't hooked up to anything, so I can, of course, touch it. I'm going to put this little cardboard backing down. And then on top of the cardboard backing, I have a sheet of paper, and the sheet of paper is has a hole. Put the backing down. We're going to sprinkle the iron filings on there in a second. Next, I have some test equipment here. We'll talk about more what this is all doing later. Here we have a power supply. We can supply current through there, and we have the scope and the function generator here in a minute we'll use to drive the electromagnet. We have a few things we're going to do. First, we're going to drive a direct current through this wire. So I have the black lead, which I'm just going to clip down below onto the bottom of the wire. This is a bare wire with no insulation. And then the top one here, I'm going to, I think, put it right here. All right, so I'm going to clip that. Now that we have electric current flowing in this wire right here, you can see over on the power supply over here, we're sending 9 amps of current. So if you know anything about electricity, 9 amps of current is a lot of electric current. So never, ever, ever try this kind of thing at home. It's something that I don't want anyone doing. That's why I'm doing the video, so you can learn from me doing it and you don't have to do it yourself. So 9 amps of current. Now this wire is now generating a magnetic field around it. So we have here a compass. When we bring the compass close, we can see that as I move the compass around the wire, it is now affected by the magnetic field. We'll come on this side. You can see as I go around, here, it's pointed in that direction. When I go here, it starts to move, and when I go around the other side, it's pointed in another direction. I actually have a separate compass. I'm going to show you 2 different compasses so we can just make sure the effect is real. All right, here's a separate compass. I just wanted to do it with 2 compasses just to show you. So here's the compass when I bring it close to the wire. Look what happens when I bring this thing and follow it around the wire. You can see it's clearly affected by some sort of invisible field, which we call, of course, a magnetic field. Around the wire there. If I were to disconnect this, okay, and there's no other magnets around, this is what the compass is doing without any current flowing in the wire. You can see I can move it on both sides, and effectively it's pointed towards north. As soon as I put electric current through this thing, then of course it's being deflected quite a bit as I move around there, right? Of course, the more electric current we're going to learn, the higher the magnetic field, so the more deflection on a compass we have. So the next thing we want to do is see what does this look like, right? Now we know that magnetic fields have to form closed circles. So because of the symmetry of the wire, there's only really one way it can do that. Let's see if our intuition is correct. So we'll sprinkle these guys, right? And it's a little difficult to get it to look perfect, right? Because this is not a super strong magnetic field just with a single wire like this. You can sort of start to see it take shape, but what I'll do is I'll just tap it like this, and now we can see it. Look what's going on here. If you go very close to the wire, you can see it's forming these concentric rings here. So the magnetic field that is formed around a wire is given by what's called the right-hand rule. If the electric current is going in the direction of your thumb, then your fingers are curling in the direction of the magnetic field. Here the positive current is going through the red wire, so really the current's going down through the page, and the magnetic field is curling in a circle in the direction I have here. Now if I tap it a few more times, I can probably get it to even do maybe a little bit more clear, something like this. So the magnetic field around a wire carrying electric current is curling in a circle around the wire, all right? Okay, now we have what we call an electromagnet. So this is a fancy looking device, but basically what it is a coil of wire. So this is a coil of wire wound around a magnetic core there. So as we run the electricity through the wire, we're going to draw pictures in a little while, but what it does is it takes the magnetic field that's generated by the electricity, and because of the way it's wound, it concentrates the magnetic field inside of the coil. And so we have this steel here, so the magnetic field will be concentrated there. The more current we run through the electromagnet, the stronger the magnetic field, and so we should be able to lift objects with this, and that's what we're going to do next. So we'll hook it up here, and what we'll do is we'll connect the power supply to the terminals. Now we have really two of them. We have another one on the other side, but we won't be using that one here, and then we'll turn the electricity on and see what we get. All right, so what we're going to do is first of all, we'll take our paper clips, we'll put them underneath here, and we'll turn the current on here, the voltage, up to a maximum of 6 volts. That's as much current, the voltage driving the current here, that's as much as this thing can take. We're at 2 volts now, nothing has happened. 3 volts, nothing has happened. 4 volts, nothing has happened. And we start getting some action around 4 volts. There, here we're up at 5 volts. We turn the current down and we release them here. So we'll try it one more time and see if we can get it to attract there. And as the current goes up, the magnetic field is going up, which is concentrated inside this coil. Let's see what we just go straight up to 5 here. And of course it lifted them all up there. And we can go down to 0 and we can drop them. Now notice what's happening when we go to 0, some of the paper clips are still sort of attracted there. And that's because as the core there is magnetized, when you release the current or turn the current down, some portion of the steel or whatever material is in there, the iron that's in the steel, remains magnetized. And so you can still get a weak magnetic effect even after you turn it off. Oftentimes that will go away after a while. So let me take these paper clips away, and I'll put these lightweight discs that are down there, and we'll see if we can do the same thing. I just think these are just neat to watch. It's really the same exact demo. So we'll go up. Let's see, this is 2 volts, 3 volts. You can see the current here, 1.3 amps right here. This thing can go up to a maximum of 6 volts. It's about 2 or 3 amps there. So we're up there right around 6 volts. This is about the limit of what this thing can do, and you can see not only is it magnetized, but the discs that are down there, once they become magnetized, they are further attracting the other disc down below, as we showed in the previous demos. We can turn this off and we can release this guy, and you can see there's some residual magnetization. Let me just kind of knock these off, right? And we'll do it again. I just think it's worth doing a couple of different times. So we'll go straight up and then straight down, up and down. Now what I'd like to do is remove these and put some iron filings down below and see if we can lift those up and what that looks like. Okay, here we have the iron filings. Let's go up and see what happens here. It's 1 volt, 2 volts. Oh, starting to be pulled up. I think that's kind of a neat little demo all by itself. And up around 5.5 volts, you can see it's starting to lift it up. Now we can release it, of course. You can kind of like make a dance and go up like this, and then down, and go up again, and then down like this. All right, let me disconnect this, and I want to try to see if we can get a picture of the magnetic field inside this electromagnet. All right, now the first thing I'd like to do, first of all, we're going to turn the electromagnet back on, and we'll try to get a picture of what the field is doing here. So here I have my little handy dandy plate here. I'll shake it up here and see if I can slip this thing down underneath and see if we can get a picture. And you can see immediately what's going on here is it's pulled up like this, and you can see that the magnetic field is circular in nature down there. And as you drag this thing through, you can just see the ripple effect of the magnetic field and how it attracts the iron filings. And it's just kind of mesmerizing to watch. Now the next thing I'd like to do is turn it sideways and see if we can get a profile view of what the magnetic field is doing. All right, let's try it first with our little plate here. We're going to turn the voltage on up to 6 volts. That's about, or 5, let's do 5.5 volts, about 2 amps, 2.2 amps, something like that. So a lot less than what we had before. Here I'm going to put my little thing down here. And you can see, I can't get it too close, but you can see the magnetic field appearing right here. In fact, I think it's going to be a little easier to see. Let me grab a sheet of paper. I think it'll be a lot easier to see. So what I'll do is I'll put a piece of paper on top, shake it up, and we'll put this right down on top. And you can see the field here. It's kind of coming out and around and entering into the other side. You can see the curved nature of it like this. As we move it around, you can see it kind of sliding back and forth. Now I'd like to do the exact same thing with the iron filings here. So I'm going to open this up. I'll try to hold it steady here and see what we get. A little harder to see. The reason it's a little harder to see is because the magnetic field is strongest inside of that coil. And we're looking kind of at the side of the coil. So it's kind of coming out of one side of the coil, coming around and entering into the other side of the coil there. And that's where the magnetic field is the strongest. It's almost like there's a bar magnet here now. And notice the connection. We're going to talk about the connection between circulating currents and permanent magnets in a little bit. But effectively, the magnetic field is coming out of one end here and going into the other. Outside of this electromagnet, it's actually not that strong. It's mostly concentrated inside the coil. Now what I'd like to do is I'd like to hook my signal generator up to this electromagnet, which can't push as much current, but we can get it to pulsate and see if we can do some neat interactions with pulsating magnetic fields. All right, here we have something really neat. So here we have the electromagnet, and it's being driven not by the DC power supply, but by a function generator. So I can drive different waveforms through here. When I press the button here, I'm going to drive it with a square pulse to turn it on, then off, and so on. So what I'm going to do is I'm going to get down here. I've got the iron filings that I've sprinkled on this piece of paper. And if I can do it without messing anything up, I'm going to push it underneath the electromagnet here. And you can see that there's some residual magnetism going on from before, but it's basically off right now. Now let's see what happens when we turn the output of the function generator on. So we'll turn it on. We can see on the scope here, let's give it a second. It's catching up there. And it's a square pulse. And the period of this pulse here is, I think I put it to 2 seconds. So this thing repeats, this on-off period repeats every 2 seconds. Now, if we take a look at what's going down under here, right, you can see that the iron filings are being attracted and then repelled, attracted, repelled, right? That's just, I think, honestly, so incredibly cool. You can sort of visualize when you see it on-off like that, that the field is coming on and then off, and you can see it directly in the attraction of the iron filings right there, okay? Now let's play with it a little bit more. Let's turn the, what's called the duty cycle of this function generator. So right now it's half the time on, half the time off. So we'll change it. We'll go over here to duty cycle, and we'll change it from 50%. We'll just go down here to like, I don't know, 25% or something like that. It takes a little time to get down there. All right, so there we're at 25%, and let's see what the difference is right here. So now it's on, off, on, whoop, looks like it's off. It's off more than it's on. So for 25% of the time, it's going to be on, and then it's going to mostly be off. So on, off, and then mostly off. Then on, off, mostly off. So let's change the duty cycle the other direction. We'll go up past 50%. And we'll go to, let's see if I can do 70, just type 75%. Let's see what 75% duty cycle does. So this should flip it the other way. Let's take a look at it. So it's mostly on now, on and then off, on and then off, on and then off, and so on. So let's change the duty cycle back to 50%. So that means half of the time the pulse is on and half the time's off. Now let's change the waveform entirely from a square pulse to a sine wave. So we can go over here to waveforms, right? And instead of a square, we can do a sine, and let's see if we can detect what's happening down here. So now you can see it's raising up very gradually and then relaxing. So a sine is a much more of a smooth curve. So it's on and then off and then on, and instead of punch, 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 punch like this. All right, let's check another guy here. In fact, let's increase the frequency a little bit, or the period. Let's just play with this a little bit. Let's see how far we can draw. You know what, let's go to waveforms first. Let's try a triangle wave, see if we can detect the difference in the triangle wave. Let's do that. So you can see it's just on and then going down, just kind of a ramp up and then down. You can see the triangle wave triggered there in the oscilloscope, up to its peak and then down and then up and so on. So let's go back to the square pulse. Let's let it kind of settle down there. All right, let's try to increase the frequency. So instead of the period here is 2 seconds, let's bring the period down to 1 second to make it happen a little bit faster. So we'll go up here to period. And from 2 seconds, let's drop it down to 1 second. And let's see what happens. So on, off, on, off, on, off, and so on. So we're increasing the frequency. I actually don't know how fast we can drive this thing and see the results of it. Let's just try half a second. Let's go over here to period, whoops, period, and we'll go 0.5 seconds. And we can just see it going much, much, much faster. All right. And let's go over here and let's drop it down to 0.25 seconds. So we'll go 0.25 seconds. We're making it shorter and shorter and shorter and shorter, like that. Boom, 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 boom. Now let's change it to a sine wave just for giggles. We'll go to waveform. We'll change it to a sine wave at this higher frequency. We can see how it's going up, down, up, down, up, down, up, down, like that. All right, let's go back to a pulse. And of course we can, now that we're increasing the frequency, we need to change our scope so we can see it a little bit better. All right, now let's go over here to waveforms. Let's go back to square wave. And instead of 0.25, let's go to 0.1 seconds. So 1/10 of a second here. Ooh, look at that. Boom, 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 boom. It's like a beating heart, super fast beating heart. All right, how far can we go? I actually don't know. 0.1, let's go 0.05, I guess. 0.05, that's cutting it in half again. Let's see what this looks like. Seconds. Whoa, check it out. It's fluttering. Oh, that's so neat. I have not actually practiced this ahead of time. I mean, I did it, but I didn't try all the different frequencies. Let's drop it from 0.05 to 0.03. 0.03 seconds. And now it's just so fast that we can't even really tell. Let's change it to a sine wave and we'll wrap it up. We'll leave it at this frequency. We'll change it to a sine wave and see what we have. And it's so fast. It's flickering. It's so fast that we can't really discern it. All right, so let me shut it down and we'll go ahead and conclude. Now I have to say I'm super pleased with this and I had a lot of fun doing these. I had done some of them ahead of time, but not all of them, and certainly didn't do the very high frequency business we just did here. So I was surprised myself and excited by it. So what I want to really drive home is that magnetism and electricity are really two sides of the same coin, really. And that's why you hear electromagnetism thrown around so much. Electric current can generate a magnetic field. Later, we're going to learn that a magnetic field can actually generate an electric current also. That's not part of what we've done here, but it's something we'll do later, right? But I want you to understand that understanding how a coil of wire concentrates a magnetic field inside of it is how a lot of our modern technology works. Motors, generators, and other devices run on this concept. And as we talk about permanent magnets, which we'll do in just a few minutes, we're going to talk about how the motion of the electrons are mimicking little coils of wire, so to speak, to generate the magnetic field in a permanent magnet. So let me take the demo equipment down and we'll draw some pictures of magnetic fields and tie everything together that we've learned through the demos. All right, so here we want to put everything together. First, let's draw a picture of a bar magnet and the magnetic field, and we'll go from there explaining everything that we saw here in our demos. So here we have a bar magnet. So we're just drawing a picture of what we have seen many times in the demos here. Now we've said that there's a North Pole and a South Pole. These are just labels though. One end is different than the other end essentially. And we have seen the magnetic field from these guys. And so we know that it comes out of the North Pole and into the South Pole. Now there is a direction associated with magnetic fields. Now really it's also occurring inside here. So I could kind of draw some dotted lines here. Usually you don't draw it inside though. And so the lines come out of the North Pole and in to the South Pole like this. So out of the North Pole and into the South Pole. If I wanted to draw more lines, I could certainly do that. I could say, well, we've got another one coming out here, a little bit nearby. And as we get farther away from the magnet, if I were to draw another one, it would have to be even farther away because remember the density of the field lines, the flux density, tells us how strong the magnet is. So out here, things are not so dense, it's fairly weak, but when the lines get crowded, we know that the magnet is stronger there. So we have more field lines coming out here, of course, making very large loops, and then making their way, back into the South Pole. So I'm not drawing these closed loops, but all magnetic fields must form closed loops. That's one of Maxwell's equations. It's always true for magnetic fields. All right, I've danced around this a few times, but I want to explicitly say, we're going to explain why magnets attract each other and repel each other. So in order to understand that, you have to understand that this magnetic field is called a vector field. You can see if I pick two random points here, then locally the magnetic field will be going in a different direction here as it is, for instance, right here, or here compared to here. They're pointed in different directions. So the strength or the density of the lines matters for the absolute strength, but the direction matters also. Because when you bring two magnets together, their magnetic fields add together as vectors add. And that is going to explain why they, or at least one way of explaining why they attract and repel each other. So we're going to get back to that a little bit later. Just remember they're vector fields. They're little arrows pointed in different directions. Now, in addition to the bar magnet and the magnetic field that we know exists around there, we also did a demo where we ran an electric current through a wire. So we're going to draw that real quick. So we had a cardboard kind of platform. This is my best way of drawing that, kind of like looking like this, like here. And that platform had a wire, which was, I think I'm going to use a different color, had a wire going up, which was copper. And I clipped electrical terminals and we ran an electric current through there. Now, for the purpose of this example, let me pretend that the electric current, or the current I should say, is flowing up. I'm going to talk a little bit more about current in a second, but let's say the positive current flow is in the up direction. The magnetic field in a wire follows, as I mentioned before, the right-hand rule. What you do is you put your thumb in the direction of the positive current flow. Again, I'm going to talk a little bit more about current in just a second, because I know you probably have questions about what's positive current flow. Just hold on to that question for a second. You put your thumb in the direction of the positive current flow and your fingers curl in the direction of the magnetic field. So if my thumb is in the direction of the current flow, my fingers curl around this wire, and this tells me the direction of the magnetic field circulating like this. And so if I wanted to draw those, then it would be down here. I'll just try to draw it in the plane here. It would look something like this right here, and the arrows would look like this, because remember, their magnetic field is a vector field. The arrows matter. So if you look at my fingers, they're circulating in this direction. Now, as I get farther away from the wire, the magnetic field gets weaker. It's still in the same orientation, it just gets weaker, and we represent that by a wider spacing between the circles. So as I get farther, I'll draw one more, maybe out here. As we get farther away from this wire, the spacing between the circles that are surrounding the wire get farther and farther apart. So the spacing between the lines tells us how strong the field is, and they get more and more crowded as we get close to the wire. The field is stronger closer to the wire, but notice they're all circulating in the same direction in accordance with the right-hand rule. All right, let me talk a little bit about current flow. So when you take my engineering class, we talk a lot more about this. We know that in matter, the way that we make electricity and electronics, the actual charge carriers are actually electrons. Electrons are surrounding the atoms. Electrons are actually moving, hopping from atom to atom. So if you visualize a long series of atoms in a wire, for instance, copper wire, the outer valence shell of those copper atoms have a lot of what we call free electrons. They're electrons that are not very tightly bound to the copper atoms, essentially. There's a lot more details we could get into that, but that's a good picture for now. And as we apply a voltage, or an electric field, across the wire, it pushes one of the electrons to the next atom over. But that displaces another one, which is also pushed to the next atom over, and it's a chain reaction. You can imagine trillions of the electrons in lockstep moving to the next atom over. So that is what we call electric current flow. That is the actual charge carrier. But mathematically speaking, it's the same exact thing to think of a negative charge carrier moving this way as if it were an imaginary positive charge carrier moving the other way. Let me say that again. Negative charges moving this way is the same thing mathematically as a positive charge moving this way. And all of our equations in physics and engineering, electrical engineering, are written in terms of positive current flow because one reason is historical, but the other reason is because the equations don't have negative signs running around everywhere. So when I say the current is flowing up this wire and the right-hand rule means my thumb is in the direction of the current flow, this is the positive current flow. We call it the whole current. The actual electrons are going down, but it's okay because the right-hand rule is written in terms of the positive current flow and it predicts the direction of the magnetic field. You could do a right-hand rule for electron flow, but then what you would do is you would have your fingers curling the wrong way and you'd have to remember to flip around the direction of the field because the magnetic field really is circulating in this manner around this wire. So from now on, when I say current flow, I'm talking about positive current flow. In your mind, you can replace it and say, okay, that's just opposite of electrons flowing. It's all the same thing, and it means the same thing. In terms of, it's just another way of looking at it. You might say it's fictitious or a mathematical trick, whatever you want to say is fine with me. I didn't make the rules. I'm just trying to tell you how everything is written so you can understand it. This is positive current flow. Now, this is the magnetic field surrounding the wire. I'm not going to write too many equations down, but I want to show you what the magnetic field equation is around this wire. B is the letter that we write for the magnetic field, right? The magnetic field B, and that's equal to, I'll tell you what this means in a second, but mu naught multiplied times the current flowing in the wire divided by 2 pi r. It's not a complicated equation, that's why I want to put it on the board. I'm trying to show you what the magnetic field around a wire is because in a few minutes I'm going to write down what the magnetic field of a coil is, and then we're going to tie that to permanent magnets and how we can understand magnetism in permanent and induced magnets also. So what does this equation mean? 2 is just a number, it's a constant. Pi is just a number, it's a constant. So these are just constants. Mu naught is something called the permeability, and I'm not going to explain where mu naught comes from right now, just suffice to say that in electricity and magnetism, we have several constants that pop up in nature related to the speed of light and to Maxwell's equations. One of them is called the permeability. It has to do with magnetism. But for the purpose of this discussion, I don't want to derive where it comes from. I just want you to know it's a constant. It's a number. So this equation for the magnetic field is a number here, a number here, and a number here. These are all just numbers. It's like 3, 4, and 7, or 10, 5, 2. It's just numbers. The only variables here are the current flowing in the wire and the radius, r. That's the distance away from the wire. So the magnetic field strength at any point in space around this wire is directly related to how much current is flowing in the wire, but it's inversely related to how far away, because the r is the perpendicular distance to the wire, essentially. So if you keep the electric current a fixed constant like we had in our experiment at 9 amps, then as the distance gets farther and farther away, then the magnetic field gets weaker. This is exactly what you would predict because you're dividing by a bigger and bigger number. But if you hold the distance constant, like if you put your finger right here and increase the current to 50 amps, 100 amps, 900 amps, then the magnetic field will get stronger and stronger at a point. So this equation makes sense. It means the stronger or the more current flow we have, the stronger the magnetic field at a given point. The farther away you get from the wire, the weaker the magnetic field is. That's exactly what you would have guessed if I just asked you how it worked before, but this is what the equation predicts. It's going to be important in just a second. All right, so now we have to talk, now that we know about wires and magnetic fields, we also did demos with our electromagnet. The electromagnet that we had is just a coil of wire, and there was a core. It's wound around a core, which is just a metal that's able to be magnetized, right? So let's talk a little bit about coils. It's very, very important in modern technology because generators and motors run on coils of wires and magnets. All right, so let's talk about a coil of wire. So here is a little electrical terminal coming in, and then your coil of wire might look like something like this. Now, when I say it's wound on a core, I literally mean that this could be some metallic core, and I'm just wrapping the wire around it. That's it. Now, the act of wrapping the wire in circles, in a helical structure like that, what it does is it concentrates the magnetic field. Because we know that every little part of this wire is kind of emanating from it a magnetic field all through space in this concentric way. But by winding it in a coil like this, we are able to concentrate the magnetic field and make it stronger inside the coil. Let me show you how that works. All right, so what I have to do is draw a big version of this coil. What I'm going to do is try to make it clear. I hope I could do it. So here we have the coil. Let me draw the coil. So here is one little part of the coil. Here is the next coil over. All right, here is the next coil over. And I'm going to draw one more. Here's the last one. Here's the next coil over. All right, something like this. Now, I'm not able to, I don't want to draw it wrapping around because then that's going to make the diagram too cluttered. Just know that what's happening is this is going here and it's connected to here and then here, connected to here, here, and then connected to here. I just don't want to clutter the diagram. I'm only drawing sort of like the parts of the coil sticking out from the board. All right, and what I'm going to do is run an electric current through this coil. Anytime you see an X with a circle, it means the current is going into the board. And anytime you see a circle with a dot, it means the current is coming out of the board. It's coming out of the board, then into the board, then out of the board, then into the board, out of the board, into the board, out of the board like this. So it's making the coil that we are drawing up here. Now, what is going to happen in terms of the magnetic field? The right-hand rule, right? The right-hand rule says we put our thumb in the direction of the current flow. The current, when it comes out of the board here, is coming straight towards you. My thumb is pointed towards you, and the magnetic field is in the direction of my curling fingers. That means that there is a circulating magnetic field in this direction. But this one's coming out of the board also, and so we have the same thing here. Now, where the current is going into the board, the right-hand rule says our thumb goes into the board, and the magnetic field circulates in this direction, right? So it's still a circle, but it's going the other way. That's very important for you to know. So it's still a circle, but it's going the other way. It's still a circle, but it's going the other way. It's still a circle, but it's going the other way, right? Into the board, circulating like this, every time the coil goes into the board like this. All right, but notice what's happening. These coils are very, very close together. Notice how tight it was wound on our coil of wire. Also, transformers are the same way. They're coils of wire that are wrapped like this and very close to each other. The wire is very thin and it's wrapped very, very close to each other. So even though I've drawn these apart, really they're right next to each other. So what you have, remember, this is a vector field. Vector fields mean the direction matters also. So if the field is going down right in this location, then right next door the field is going up. What happens right between these coils? In between these coils, I'll draw it in this. In between these coils, they cancel. Right? In between the coils, they cancel. And what happens up here? I'll draw it right here. They cancel. Right? Why? Because right here I have a magnetic field going up, but right here I have a magnetic field going down, and they're right next to each other. So they add up. Literally, it's like a rope where one person is pulling one direction and the other person's pulling the other direction. If I'm pulling the same force, but in two different directions, they cancel and the rope doesn't move. If a magnetic field is pointed this way and then right on top of it, another one is pointed with the same strength in the opposite direction, they add to zero. And so there's zero magnetic field in between there, right? But look at what's happening on the inside of the coil. This magnetic field is pointed this direction, and this one is pointed this direction, because remember, these are circular, so it's kind of like the arrow is like this. But look where these arrows are going this way, and that means this one's pointed this direction as well. So if the field is here, and here, and here, and here on the inside of the coil, it's in the same direction as they're all pointed right here. So these magnetic fields are all lined up in the same direction, and they're aligned in the same direction here. So what you're actually going to have is you're going to have a uniform magnetic field on the inside of this thing, and it's going to be pointed in this direction. So I'm going to try to draw equally spaced lines here, like this, because you can prove mathematically, I'm not going to do it for you here, but when you have an infinitely long coil like this, then the magnetic field on the inside is everywhere uniform. And it's uniform because all of these coils are putting a magnetic field inside in the same direction, so they all add up together. And in between the coils, they add up to zero. Now remember, magnetic fields have to always form closed loops, always. So what actually happens is, it's kind of like, it'll be like this. It'll be right next to here, and then it'll loop around and connect back like this, right? So this will be here, 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 and these, of course, will be in this direction right here, right? And here, you have the same exact thing. We have one right here, and it's going to loop around right here, right? Like this. And then these are in the same direction like this. Right, now what about these in the middle? How do they close in? Well, what's really going to happen is these are going to exit and make very, very big circles to the outside. I don't have enough room on my board, but you get the idea. They're going to make very, very big loops coming around to the other side. Now here is the kicker. Here is the most important thing. If you make what we call the ideal coil or the ideal solenoid, ideal means you can pack these turns very, very close together and you make the coil of wire infinitely long. Okay, we can't really build an infinitely long coil, but what if we made it really, really, really long compared to the diameter of the coil? Like if the diameter were the length of the diameter of this pin, what if we made it like 5 meters long with the diameter of this pin? That would be a really long coil compared to its diameter. You can show mathematically that if you make an ideal solenoid, or an ideal coil, is what it's called, is a solenoid, when you make an ideal solenoid, you can show mathematically that the magnetic field inside is high, where the magnetic field outside is exactly zero. There's no magnetic field linkage. Now, in reality, it's not really zero outside because you have to have closed loops. But remember, I said it's an infinitely long coil. That means the coil goes to the end of the universe, which we can never have. And so you would have magnetic field lines that would be going like past Alpha Centauri to come back. So that's just an idealization. You can't have that. But in an ideal solenoid, the magnetic field is high on the inside and zero on the outside. It's concentrating the magnetic field inside the coils. Now, what is the equation for the magnetic field here? The magnetic field in this coil of wire is equal to the same permeability that we talked about earlier, multiplied by the current flowing in the coil, again, positive current, multiplied by N, which is the number of turns per unit length. In other words, N is not just the number of turns, it's the number of turns per meter or something. How tightly you can turn the things is what this is. And this is the magnetic field inside, and the magnetic field is zero outside. And this is for the ideal coil. Now, what does this tell me? This tells me that if I make a very, very tightly wound coil with tons and tons of turns per unit length, per meter or whatever, very, very, very tight with super thin wire, then I'm going to have a high magnetic field on the inside. If I put a lot of current through that coil, the more current I put, the higher the magnetic field direct relationship. Right? And there's no dependence on the distance inside. There's no R, like we had over here, for the magnetic field around the wire, we had the distance from the wire. There's no dependence on distance here. So that means that in an ideal solenoid, an ideal coil of wire, infinitely long, as we said here, then the magnetic field on the inside is uniform. There's no dependence on distance because it's uniform. And what's happening is you have the field canceling on the outside and adding up on the inside. Because when you really think about it, this part of the coil is pointing to the right with its field and to the left right here. So you have pointed to the left right here and to the right here. This on the outside is pointing to the left. As we get farther and farther away from this coil, we can have a field pointed to the right to cancel any field pointing to the right here. So you get a small field on the outside, and the reason you get a small field on the outside is because as you get farther away from this part of the coil, it's pointed to the right, and this part is pointed to the left, and so they add up along the outside of the coil to be zero, but they add up constructively on the inside. So on the outside of the coil, in an ideal coil that's infinitely long, the magnetic field adds up to zero, so there's no field outside, but there's a fixed constant field inside. All right, now you might say, man, he is really diving into a ton of detail about coils. The reason I want to talk about coils, and so you understand the magnetic field, is because it helps us to understand how permanent bar magnets work. When I was young, one of the very first questions I ever asked anybody about science was, how do these magnets work? I remember that. I think I was 4, right? And somebody started drawing a magnetic field, right? And it was just mystical to me. It's still mystical to me. And everything I'm about to tell you should hopefully illuminate you. But ultimately, magnetism is a quantum effect, and none of us have a really good gut feel and understanding for quantum mechanics. Nobody really understands quantum mechanics. So I can describe this to you as best I understand it, but none of us really get quantum mechanics on a gut feel level. So ultimately, you may understand more than you did, but you may not be completely satisfied because none of us have a gut feel for quantum mechanics, and magnetism is a quantum mechanical effect, okay, that adds up over large distances. Right, so I want to, and the nature of the coil of the wire generating a magnetic field is going to be analogous to electrons generating the magnetic field inside of a solid. So before I get to that, I need to do some talking, right? I need to do some talking. And I have a lot of stuff on my paper. Some of it I'll write down, but most of it I'm just going to talk through it, because if I just start writing, it's going to be writing and writing and writing. I don't want that. I just want to explain it to you. All right, so we have magnetism in matter, right? When we talk about magnetism, mostly what we're talking about is ferromagnetism. Ferro has the prefix ferromagnetism, which means iron. Ferrous means iron, right? Some of the first magnetic materials, very easy to magnetize iron. And the iron filings we were using is proof of that. Very easy, the most common thing we have to really demonstrate magnetic effects. What is ferromagnetism, right? What it is, or what is a magnet, right, in general? What it is essentially the electrons that are inside of the atoms in some materials can be aligned in such a way that the magnetic fields that are individually contributed by all the different electrons can align up, so they can add together to make a larger magnetic field that can emanate from the bar magnet. Let me say that again. In ferromagnetic materials or permanent magnets, like we have talked about here, when they are magnetized already, what has happened is on the microscopic domain, the electrons have been lined up, and I'll talk about more how in a second. They've been lined up in such a way that their little bitty individual magnetic contributions are adding together. And when you have trillions of them aligned in the same direction, the magnetic field is additive, creating a strong magnetic field which can then emanate from the substance. It's kind of like this coil here. Individually, in each little turn of the coil is generating its own little magnetic field, but by aligning them, by winding it in a certain way, we can force them to add together and give us a high field on the inside and very low field on the outside. In ferromagnetic materials, that's automatically happening in nature. So ferromagnetism refers to sort of two things. It's what we typically think of when we think of bar magnets, but ferromagnetism also applies to materials that are not already magnetized, but can be magnetized very easily. For instance, when I bring the neodymium magnet close to the iron filings, what happens? The iron filings start becoming attracted. Now we're going to talk about the attraction part in a second, but what's happening on a microscopic level is the magnetic field from the permanent magnet starts to enter into the vicinity of the iron. And that magnetic field causes the electrons in the iron to be aligned so that their magnetic, what we call magnetic moment of the individual iron electrons that are in there, can become aligned in an overall same direction. So essentially what we're doing is we're causing the iron filings to become magnetized. When we say become magnetized, what it means is we begin to align the magnetic directions of all the atoms in the iron. Once they're aligned, they form sort of their own little magnetic domain, is what we talk about, and then the two magnets can be attracted together. The iron filings fly forward and then hit the magnet. So it's a two-step process. The magnetic field permeates the iron, aligns the iron's electrons into a common direction, and so then the magnetic fields are additive. It turns it into a magnet at that point, and then because you now have two magnets, they can be attracted to each other, and then we have the attraction effect. Same thing with the paper clips, same thing with any material that can be very easily magnetized. We call it ferromagnetic. All right? When we apply a magnetic field to a ferromagnetic material, it gains a very strong magnetic moment, is what we say. When we remove the magnetic field, another characteristic is it begins to retain some of its magnetism. And so that's a characteristic of ferromagnetism as well. So if you notice, when we magnetize the paper clips, even after we turn the electric current off, we still had the paper clip hanging there. That's because it's a ferromagnetic material. Once the alignment happens, even after you remove the external stimulus, the atoms are still aligned weakly, okay? They're not a strong magnet, but they are still aligned, and that's why they were still being attracted even after we turned the electric current off, or the iron filings were still attracted even after we kind of moved them off to the side and they weren't no longer interacting with a magnetic field. So ferromagnetism is a phenomena where matter can be magnetized by microscopically aligning the electrons in such a way that I'll talk about in just a second. And that creates an external magnetic field, and then the two items, it can be attracted to a magnet. And even after the magnetic field is removed, it retains some percentage of the magnetic moment that it had. And eventually what happens is the material everything is at a certain temperature, at room temperature. And different materials behave differently, but basically the thermal collisions of the atoms inside slowly begins to destroy the magnetic alignment. And that's why they don't stay magnetized forever. Now, some materials, if you form a magnet properly and you put it in a very strong magnetic field, it can retain its magnetic moment for a long period of time. But the paper clips we were dealing with, they were weakly magnetic after we turned the electromagnet off, but they're not going to maintain their magnetism forever because thermally, the atoms are being agitated constantly and they're going to re-randomize the magnetic moments of the material, of the electrons that are inside of there. All right, so I've been dancing around a bunch of things because this is really a quantum mechanical thing and I can't get too far into it without bogging us down in a lot of theory. But in general, that is what is basically happening with ferromagnetism. Any bar magnet that you see that's given to you that's already magnetized, it's a ferromagnetic material. It's already been aligned with a very strong magnetic field in the factory. We have materials in the ground. We pull them out of the ground. They're already magnetic. How do you think they're magnetic? Because the Earth is a gigantic magnet. We have a magnetic field and it can align the magnetic domains there, and it can create permanent magnets in the ground. Some of the first experiments with magnetism were done by pulling rocks out of the ground and figuring out that they can attract things, right? Attract and repel weakly. If you remove the magnetic stimulus, they retain their magnetism for some period of time, but thermally, they will eventually lose it. And if you heat them up beyond a certain point, they'll completely lose their magnetism because the collisions thermally will re-randomize the electrons that were aligned inside of the material. All right, let me read my notes and make sure. Magnetism, all magnetism, is purely a quantum mechanical effect. You cannot explain it in terms of what we call classical physics. Quantum mechanics was invented in the very early 1900s. It explains so many things and enables all of our modern technology, from phones to communications equipment to computers to satellites. Quantum mechanics is everywhere. It also governs magnetism. And if you don't care about that, I mean, that's fine, but all of our power generation comes from magnetism as well. So it's kind of important that we understand a little bit of quantum theory. But it is a quantum effect. All right, magnetic materials that we call ferromagnetic, iron, obviously, because of ferro, it means iron, cobalt, and there's several others as well that can be have a strong magnetic field and retain their magnetism after we pull it away. All right, so now I think what I want to do is I want to talk a little bit more detail without trying to bog us down too much into what it means to align these electrons. All right, this is going to be a little tricky because it's a quantum effect, and so I'm going to draw pictures that are not true quantum pictures, but they can still give us the idea. Remember that we said that basically if you have a coil of electrons that are circulating in this coil, what we can do is we can get a concentrated magnetic field inside the coil. So if you just forget a coil, just consider a single electron moving in a circle. Like if you could just grab it with your finger and move it in a circle, it should generate a magnetic field pointed in a certain direction. What would that look like? Right? That's what I want to talk about next. What would that look like? Let's say we have an electron moving. I'm drawing kind of a side view here, kind of in this direction like this. Right? And that means at one moment in time, the electron is right here. It moves this way, and then the electron later in time is right there. And these arrows are not magnetic fields. It's the direction. I guess I'll shade them so that we don't get them confused with magnetic fields, right? It's circulating like this. In other words, imagine it just kind of going around in a circle like this. And we know that moving electrons generate magnetic fields. How and what direction would it be generated in? Well, first of all, I want to talk about something called angular momentum, right? Or spin, right? So the spin axis of this thing, you could think of the spin axis of this thing, call it S, or the angular momentum. In the direction of travel, you have an angular momentum pointed perpendicular to however the thing is rotating. We call that the spin, or you can also think of it as angular momentum, right? If I wanted to figure out how the magnetic field was pointed here, I would use the right-hand rule. But remember, the right-hand rule deals with positive currents. Everything has to be reversed when you're talking about electrons. So if I put my finger into the board, if the thing is going this way right here, that would be positive current flow, but the electron is really going in that direction. So what I would do is I would turn my finger around and say the positive current would be going the opposite direction of the electron. Remember, the right-hand rule thumb points in the positive current flow. So if this thing is going like this, it's going into the board here, but then I have to turn it around because the positive would be going in the exact opposite way. That would mean that I would have a magnetic field circulating kind of like this around. It would basically be going down and then kind of like back up through here, right? At this point in time, if again, it's coming out of the board, which means I go into the board here, then I'm going to have a circulation and a magnetic field that's going to be going down like this, and then this way it's going to be going the opposite way. It's like one little loop of the coil that we had just talked about right here. And notice that these are kind of additive, so we get a strong magnetic field in the middle and a kind of a weak magnetic field everywhere else. Now, if you can, this is why I said I'm lying to you a little bit, because electrons are not little balls. Okay, electrons obey wave mechanics from quantum mechanics, but you can still think of them classically as little balls, and it helps us visualize it, but just know that I'm lying to you a little bit. They're not little balls. But classically, we can envision them like this, okay? So don't get too mad at me. I'm just trying to make it easy for you to understand. If we make the radius of this thing smaller and smaller, but keep orbiting this electron, then what's going to happen is we're going to get a very concentrated magnetic field on the inside as we get it smaller and smaller and smaller. What happens if we make the radius of the thing so small that really it's not orbiting, it's just like a ball rotating? Would the electron have a magnetic field associated with it? The answer is yes. Every school child learns that electrons and protons have charges and they repel, electric repulsion. Either they repel if they're the same charge or they attract if they're opposites. Opposites attract, right? But most school children are not taught that electrons also have a magnetic field associated with them. We can measure it very, very accurately. It's called the magnetic moment of an electron. And even though we know electrons are not balls that spin, we can still envision it in this thought experiment, an orbiting electron getting smaller and smaller and smaller. Eventually, what it is just a single electron that is kind of like rotating, even though it's not rotating. But if you had the radius of it getting smaller and smaller, eventually it rotates, then there should be a magnetic field associated with this. And the magnetic field that we measure for electrons is a fact, and it behaves kind of, as you can think of it, as an electron spinning. So we say that electrons have spin. Now, it doesn't really mean that electrons are balls that spin. What it really means is electron is this thing that nobody can really visualize, but it obeys wave mechanics, and they have angular momentum, which means they have a spin axis, and they have a magnetic field oriented in a certain direction, somewhere along the line of that spin axis, right? So if we do the right-hand rule and figure out that these things are essentially, if it's kind of going this direction, the magnetic field is pointing down in the center here. If you shrink the radius of this thing, then I'm going to take the little arrow away, and I'm going to put I guess I'll put it here. This is an electron, right? Here, then what we can say is that electrons behave as if they are spinning, and they have a sort of a magnetic field that emanates from this, or from them, and as you might guess, looks something like this, right? Now, this is not an exact picture or anything like this, but essentially they behave like this. So you have pointing like this, pointed like this, right? If you look at it, it's almost like down and then up. But if you shrink it down, it's like along the spin axis, it should be pointing down. And so along the spin axis, it's pointed down. And so they're coming down out like this, right? And they kind of go back into the other side. So it's sort of like just shrinking down this concept right here. So there's a lot of things going on inside of an atom. We have electrons surrounding the atoms. Those electrons we say are orbiting. But that picture of a solar system of orbiting like planets is not really true, but it's still good for us to visualize the general idea. There is an angular momentum of the electron cloud around an atom. That's what we can say is true. And that contributes to some magnetic effects. But more dominant than that is that the electron, even just by itself, spins all the time. Now, it's not really a ball spinning, but it has angular momentum, right? It has angular momentum, and so it has a spin axis we can label here. And then it has what we call a magnetic moment, which is going to point down. This magnetic moment of the electron points down. We call it mu sub s. This is the magnetic moment of a single electron by itself, not near an atom, not near anything. It appears as if it's a spinning ball. It's not a spinning ball, but that's a good way to think of it. And it has a magnetic field oriented opposite to the spin axis. The reason it's oriented opposite is because the right-hand rule is for positive charges, but electrons are negative, and so the axis is flipped opposite. Exactly why I spent time on the right-hand rule earlier. So in ferromagnetic materials, what we say, or what the theory is that the electrons that are in all of the atoms in a ferromagnetic material are very easily, or much more easily, able to be aligned. What it means is the spin axis of all of these electrons are able to be aligned. And that means the magnetic moments and the magnetic fields are all able to be aligned. So if you can imagine trillions of these electrons everywhere in the material, and they're all lined up like this, then the magnetic fields will be additive, just like they're additive inside of the coil, and then they'll eventually exit the whole thing and come back around and enter into the other side. And this is why if you break a magnet in half, there's a north and a south pole. So you think, okay, I'll just break it in half. What will happen? Well, then you have a new north and a south pole on each piece, because there's not just a north and a south pole. There's almost an infinite number of north and south poles. All the little electrons are forming kind of a tiny little north and south pole bar magnet. You can almost think of each electron almost being like a little bitty bar magnet inside. So if you break it in half, all that's going to happen is the field lines are going to connect to wherever it broke off. So you can never get down to a single, you'll always have closed loops, I guess is what I'm trying to say, even if you break the bar magnet in half. All right? So the picture that we often draw is in a ferromagnetic material, right? Like a bar magnet or something like this. Then below a certain temperature, or if it's not magnetized already, the spins of the electrons are basically in all the material, they're just randomly lined up in different directions, right? But if you apply a magnetic field to this material, or if the Earth does it, because the Earth is a permanent magnet, right? Then what you can end up doing is you can end up aligning them in the same direction. Now, in reality, they're not all lined up in the same direction, because remember, everything is at a certain temperature, everything's being agitated. So thermally, there's collisions happening and things are being knocked out, but still there's an overall alignment happening in aggregate across the material. And that makes the magnetic field emanate from one side to the other. And it's because of the quantum mechanical nature of electron behavior. So there's a tiny contribution from the orbiting of the atom. We call it the orbital angular momentum, but there's a larger contribution to the spin angular momentum of how electrons behave. So that's what effectively ferromagnetism is. Any bar magnet has already been aligned and it retains that magnetism. But if you heat it up too much thermally, it'll start to be unaligned again, and you can demagnetize a magnet that way. All right? Now, let's talk about, let's see, I talked about that. Let's talk about another kind of magnetism you may have heard of called paramagnetism. So the prefix para, I looked it up, it can mean lots of things, like 10 different things, but it can mean beside, it can mean near, beyond, or abnormal. So think of paranormal as like abnormal. So paramagnetism is sort of like abnormal magnetism, or you can think of it as near magnetism. There's many different meanings for the word para. Paramagnetism is simply induced magnetism. Just like we can take ferromagnetic substance and line them up and they'll retain their alignment because of I've kind of skipped over a lot. The reason iron can do that, the reason iron can be aligned that way is because of the way the electrons are paired up in the material. At the quantum structure of the electrons orbiting the atoms are paired up in such a way that allow them to be aligned like this. Most materials cannot be lined up like this, and so most materials are not magnetic at all. Well, at least they're not ferromagnetic. Many materials can be what we call paramagnetic, which means that if you apply a magnetic field to them, they can be aligned, but only weakly. Right? And when you remove the magnetic field, they immediately go back to their random state and they're unmagnetized. Many materials are like this. Examples are tungsten, aluminum, lithium. Typically, if you put a magnet next to an aluminum can, it won't be magnetically attracted, but aluminum is weakly paramagnetic. So if you put it in a strong enough magnetic field, it will align and turn magnetic, but only weakly. Again, the electronic structure of the electrons orbiting the atoms govern this behavior. It's beyond the scope of this lesson, and you study quantum mechanics and chemistry, we'll learn exactly in the electron configuration why some materials are magnetic and some aren't. But it has to do with how the electrons are in the orbitals of the atoms and how they're paired up. So, paramagnetism, alignment of the magnetic moments of the electrons when an external magnetic field is applied. But again, it's a weak alignment, and when you turn off the external magnetic field, the effect goes away, and so then it just loses all of its magnetism. All right, we could talk about paramagnetism and ferromagnetism forever, but I think I want to be done with that for now. I want to tackle the concept of why do magnets attract and repel. I'm going to say right now that no matter what I tell you, someone is going to email me and say it's wrong. And that's because there's multiple ways of thinking about why this effect happens. Ultimately, magnetic attraction is purely a quantum mechanical effect. And we don't have everyday experience with that, so everything at the quantum level seems like it's unnatural, but in fact it is natural because everything is made of quantum objects, ultimately, right? But the way I'm going to teach you about it, I think is a good way to think about it, but just know that there are other ways to think about magnetic attraction. You can even use Einstein's theory of relativity, believe it or not, to describe magnetism. Now I'll do that maybe another day. But for now, I want you to have an intuitive understanding why magnets attract each other and how they can repel each other. All right? Before I do that, I need you to understand something. The magnetic energy density. I promise it looks complicated, but it's actually very, very easy to understand. Magnetic fields store energy, right? They store energy. And when you can extract some of that energy in some of our modern devices like generators and things like that. But they contain potential energy. Electric fields also store potential energy. So the equation that governs that is the following. The magnetic energy density is equal to the magnetic field strength squared divided by 2 times this constant, the permeability, which I mentioned several times applies to magnetism. The only thing I care about you knowing, I don't even care about the units, although I'll tell you that the units is basically going to be joules per some unit volume, right? It's an energy density. So the magnetic field, you square it, and then you divide by 2 numbers. This is a number and this is a number. So basically the energy density is just related to the magnetic field strength squared. The higher the magnetic field, the more energy it stores, right? We can build electronic devices, coils of wire that store lots of energy in magnetic fields that can be released in other situations, right? In circuits, for instance. The best way to think about stored energy is a rubber band. If I pull a rubber band, I'm storing energy in that rubber band. How is it stored? In the electric attraction between the atoms, which are now being stretched apart. It's wanting to pull them back together. So there's energy stored in the electric field between atoms and electrons, and there's energy stored in the magnetic field that exists in space. And where the magnetic field is strongest, then the energy is going to be higher. So if you think about it, around this wire, out here far away, the energy stored in the magnetic field is small, but the energy density is very high, very close to the wire. The magnetic energy density is very high inside of the coil, but very weak outside for the same reason. Now I need you to understand that in order to understand why magnets attract and repel each other. So here we go. It's going to be easy to understand, I promise. Here is a bar magnet, right? Here is another bar magnet. All bar magnets have some north and south pole. I'm going to draw this one north-south. I'm going to draw this one north-south. Now, how are these things going to behave? Same poles are going to repel each other. We know that to be the case. Let's draw the magnetic field, not the whole field. We'll just draw kind of a little portion of it. It comes out of the north, goes into the south. So this way, this way, this way. It goes out of the north, into the south, right? This one is going to go this way, and it's going to connect again to its south pole, out of the north, like this, and in to the south, right? Now what's going to happen as we push these things closer together? Notice that the direction of these arrows are kind of pointed at odds with each other, but the closer I get them, what's going to happen is they're going to be sort of additive. Yes, you can think of it as a vector. You can think of it, some of it pointed this way and some of it pointed up. So you are going to have a cancellation in the portions that are pointed at each other, but you are going to have a portion pointed up. And as you get them closer together, that's going to get bigger and bigger and bigger. So they're going to be additive inside. They're in general pointed in the same direction. So you're going to have strong field inside of here as you push them together, because you can see they're sort of pointed, not exactly in the same direction, but as they get closer together, they're going to be more and more, if you can think about the ones coming this way, they're going to be aligned up more and more, and it's going to get very, very strong magnetic field in the center. But the stronger the magnetic field, the more energy is stored. So you have to think about, how does the universe operate? The universe operates by going from high energy to low energy. This marker has potential energy from the gravitational field of Earth. Here it is at a high potential energy. When I let it go, it's going to move down to a lower potential energy because it's closer to the ground. Everything in general wants to travel towards lower energy. If you start asking me questions like, well, why does everything try to go to lower energy? I am sorry, I can't help you, but that is how our universe works. The rules that are in place are that things tend to wind down towards lower energy. When you drop things, they go from high energy to low energy. When you have temperature, a very hot cup of water, it tends to cool off because it's going from high energy, high movement of the atoms, to low energy, low movement of the atoms. When you stretch a rubber band, that's high energy. You let it go, it goes to low energy state. And if you try to push these magnets together, it's going to be trying to make a stronger and stronger magnetic field in the center, which is going to raise the energy of the magnetic of the energy stored there. And the universe never wants to go to a higher energy state. That goes against the laws of nature. So when you put two magnets together, because the magnetic field's trying to get stronger in the middle, storing more energy, it's going to resist that. In other words, I have to put work in to store the energy there. Let me say that again. I have to put work in from my chemical reactions in my muscles. I have to do work on the magnets to store the energy that is now higher between the magnets. Because when I put them together and force them together and hold them there, then I've now stored energy in the field. Where did the energy come from? It came from my muscles. Where did that energy come from? It came from the food I ate. Where did that energy come from? The chemical bonds of the food I had. So the energy came from somewhere, the food, and into the magnetic field. When I let it go, they tend to push apart because the energy is then released, and everything, the universe tries to move towards lower energy states. Just like the marker goes from high to low, the child on the slide goes from high to low, the rubber band goes from high to low, the cup of coffee goes from hot to cold. High energy to low energy. That's why they repel, because as you push them together, you're trying to make the field stronger there, which means more energy there. It's like trying to go uphill on a slide. You're going to have to fight and do energy and work on yourself to climb a flight of stairs. That's just the way the universe works. Now, let us talk about the opposite situation. Let's talk about the situation where now I have two bar magnets. And instead of this, I put this as the North Pole here, and I put this as the South Pole here. You already know what's going to happen. Opposites attract, so they're going to come together. Let's see if we can understand it. The magnetic field exits and enters here, exits and enters here. It comes out here and enters here. It comes out here and it enters here. It goes out of the North Pole, always into the South Pole. So out of the North Pole, always into the South Pole. And then it goes out of the North Pole here, out of the North Pole here, and this direction, and into the South Pole here, into the South Pole here. Now I'm going to erase this one because I think this makes it confusing. But you can see the arrow. Actually, let me erase this one as well. I think it's going to be a little clearer if I put, yeah, like this, like that. So like this. Notice the direction of the arrows. When I bring these things closer together, notice that this one is going up, but this one at the same location is going down. They're fighting each other. And as I bring them closer and closer together, I messed up my drawing, I'm sorry about that. As I bring them closer and closer together, what is going to happen? This magnetic field is going to tend to cancel with that one and make the magnetic field strength lower. This one is going to be going the opposite direction of this one, and it's going to tend to make the magnetic field strength lower in the center here. So as I bring these guys together, I'm going to write down weaker. As I bring them closer together, the field gets weaker in strength. But weaker in strength means weaker in energy storage. And remember, the universe likes to go towards lower and lower energy storage. So two magnets attracting can be explained. Because when we bring those two poles of the magnet together, we are canceling the magnetic field, making the magnetic field lower between them, which is a lower energy state. Lower energy, it's like releasing energy from the rubber band. The same way the rubber band comes together, the magnets come together, because as soon as that energy starts to get lowered, it is just going to fly together to make the energy lower. Forces in nature generally always push things in the direction of lower energy. Gravity pushes you down the slide to lower energy. The electric forces pull us to lower energy from the rubber band, and the magnets pull each other together or push each other together into a lower energy state together where the field is weaker. You feel a repulsive force because as we try to do this, the field is stronger and we're raising the energy here, and so it wants to resist that. Okay, that is about all I want to say about it. I can talk about magnetic attraction and repulsive in other ways. You can use relativity theory to talk about relativistic effects to explain why magnets work. And I probably will do that one day because I think it's a neat way to look at it. But it's just another way of looking at it, right? An alternative way of looking at it. You can also look at the magnetic force on a charged particle, the deflection of a charged particle from the magnetic force itself, to explain why magnets attract each other. That's another fine way of doing it. I thought about presenting all of those, but ultimately I think that this is the most clear and elucidating, to use a big word, way to explain it. The universe likes to go from high energy to low energy. When you push two magnets together with the same pole, either both north or both south, the same exact thing will happen if you take this. If you can imagine the south pole over here, they're both going to be pointed in the same direction, and the two south poles are going to make a strong field, and it resists that. But if you flip it around, they're going to attract to make the field and the energy stored lower. Now, if you ask another question, well, why does the energy of the universe like to get lower? Well, I don't know, and nobody knows, all right? Or you might say, back to the electron spinning. You might say, okay, that's a neat theory about the electron spinning and how it explains magnetism, but why do electrons spin? I don't know, okay? And also, is it a ball? No, we know it's not a ball. Quantum mechanics is a wave theory. We know electrons are waves, but they have some kind of angular momentum, and nobody has a really good picture to describe how a wavy thing has an angular momentum, which we usually associate with spinning objects in the macroscopic level. Ultimately, one of my favorite people that I've ever studied is a famous scientist named Richard Feynman. Probably knew more about quantum mechanics than most people will ever learn, right? Way more than me. And somebody asked him, hey, explain to me why magnets work. And he thought about it and he gave about a 20-minute answer and ultimately concluded, I can't explain it to you because once you continue asking questions, you get down to the point beyond which anyone has any answers to anything. So all we do in science is we have models of nature, right? Do magnetic field lines exist? Not sure. They're a great calculational tool to calculate how things will behave though. Do electrons really spin? Not sure, probably not, but it's a great calculational tool. It's a good model of how the universe works. Maybe everything is string theory. Maybe everything is waving strings. Maybe angular momentum is something totally different than I can conceive of. But that doesn't make the theories and the ideas worthless. We come up with better and better models to describe the world. This is how I chose to describe how magnetism attracts and repel objects to you. When you bring a magnet next to the paperclip, it aligns the magnetic domains as we drew in the paperclip, and then now we've explained how magnets can attract and repel, and then of course they attract each other. So you're inducing a magnet to form, and then they attract each other. And then of course we talked about this. If that doesn't satisfy you, well, join the club. It doesn't totally satisfy me either, but I think it's the best humanity can do with just making better and better models to describe our world. I hope you've enjoyed this. I know it was a bit long. I thought about cutting several things out, but ultimately I thought, you know what, I'll just put it out there and see what people think. So please drop me a line, let me know what you think, and if you made it to the end, thank you very much. Drop me your thoughts, and I'll see you in the next one. Learn anything at mathandscience.com.